in this chapter, which is chapter 5 of year 2, we're going to have a look at radians. Now, all that radians are is an alternate way of measuring angles. Just like we've got lots of ways of measuring distances, e.g. we could use centimeters, or we could use meters, or we can use inches, we can use feet. In angles, we've got degrees, which is probably the only unit you've used so far, but we've also got radians, which gets used a lot in pure mathematics. Okay. Now, the most important conversion factor that you need to know is that 2 pi radians is 360 degrees. Okay, so a full rotation, that is 2 pi radians. Okay, so if I started at this point here, okay, so I measure my angle starting from this point here, and then I go around anti-clockwise like this, that'll give me my angle in radians. So if I was to do a whole 360 degrees, you can see that is 2 pi radians. If I was to just do 180 degrees, that would be pi radians. Okay. If I was to do 90 degrees, then that would be pi over 2. So maybe let's write a few of these on. This is obviously 90 degrees here. This is 180 degrees. So there's a few easy ones. 2 pi is 360. Pi is therefore 180. Pi over 2 is therefore 90. Pi over 4 is therefore 45 degrees. Okay. And you can work out other multiples as well. So, for example, pi over 6, well, that's 180 over 6, so that's 30 degrees. Okay. Now, all of the things that we know about trigonometry still work with radians rather than degrees. It's literally just another way of measuring it. So, in this lesson, we're going to look at looking at arcs and sectors, and calculating lengths and areas. Next lesson, we'll also look at solving trig equations, but giving your answers in radians rather than degrees. But it'll be the same process. If you wanted to convert between the two, as long as you know this fact, 2 pi radians equals 360 degrees, then you should be fine. So if we know that this is true, we can say that 2 pi radians, you can write over a little r, is 360 degrees. Well, that would mean that 1 radian is equal to, so I'm dividing this by 2 pi, use 360 divided by 2 pi degrees. Or you could say 1 radian is, that would be 180 over pi degrees, or if you wanted that as a number, 1 radian, 360 divided by 2 pi gives you about 57.3-ish. Okay, but that's approximately, that's not an exact value, so I wouldn't use that for converting. If we want to go the other way instead, so we want to know what 1 degree was worth, so we could divide it by 360, and that would mean that 2 pi over 360 radians is 1 degree. 2 pi divided by 360, that is about 0.017 radians is 1 degree, but that's probably not as helpful, is it? Okay, so as long as you've got this fact, 2 pi radians is 360 degrees, you can use that to convert between the two. So you can work out, well, 1 radian is this many degrees, or 1 degree is this many radians, and you could use that to help you. Okay, before we look at arcs and sectors, it's worth just going over a bit of terminology to do with circles. Let's look at this first one here. Hopefully these ones we should know. So we've obviously got the center here marked as O. Then we've got the diameter. So the diameter is the full width of the circle which goes through the center. The radius is obviously half of that, but the important thing is it goes through the center. A tangent, we know what a tangent is. It only crosses the circle at one point. You should also know that a tangent meets the radius at 90 degrees. That's another useful thing. A chord joins 2 points on the circumference, so 2 points on the edge of the circle, but it doesn't go through the center. So this line here is a chord. On here we've got some arcs and some segments. So this bit here, I'm just going to highlight it. The edge of the circle is what you would call an arc. And you can see here the big arc is called a major arc, and then the smaller one is called a minor arc. Okay, but that is the edge of the circle, so it's like a portion or a fraction of your circumference. This orange line we talked about that a second ago. That's a chord, and the area formed by this minor arc and a chord is a segment. Okay, or in this case, we've got the minor segment, and then we've got the major segment, the big bit and the small bit. Here again, we've got some arcs, but rather than being divided by a chord, it's now divided by the radius. This is the radius here and here. And this section here is called a sector. Okay, so a segment has got a chord, whereas a sector has got the radius here, so it's divided from the center. And this is what we mean by a sector. Okay. And that's what we're going to look at in this lesson, is sectors and arcs mainly. And we'll also have a little look at segments. Okay. First of all, we're going to look at how we calculate the length of an arc. So if I mark on the center here, we're going to find maybe the length of this arc here. Okay, so I want to find that curved length there. Well, if we say that the angle is theta and the radius is r, let's think about how we would do that in degrees. Okay, and then we'll think about how we do it in radians. So in degrees, well, this length here, this is a fraction of the circumference. So the circumference would be 2 pi r. That's the formula for the circumference of a circle. And we want a fraction of that. So we just want this little section here. The fraction I want is theta out of 360 degrees. Okay, so we're just doing it as a fraction of a circle times 2 pi r. If we do it in radians, we can use the same idea. So we can use 2 pi r, so that's the circumference, times, then we want the fraction, which is theta, over, but instead of 360 degrees, it's going to be 2 pi radians. Okay, and now hopefully you can see if I can simplify this to 2 pi r theta over 2 pi, which just gives me r theta. So the arc length, when you're working in radians, is just r theta, which is a really nice short formula. Okay, so you can just use the radius times the angle, as long as your angle is in radians, to find the arc length. Okay. Now, if we do the same for an area, we'll draw the same sort of diagram. So I've got my angle theta, I've got radius r, but this time I want to find the area of this sector here. Okay, so I want to find that area. If we do it in degrees, then we're going to have pi r squared, that's the area of a circle, that'll be for the whole circle, and we want to times it by theta over 360 for whatever fraction of the circle we want. In radians, if we do the same thing, we're going to have pi r squared times theta over 2 pi, which again I can simplify that to pi r squared theta over 2 pi, and you can see the pi's cancel out here. So I'm left with r squared theta over 2, or you could write that as half r squared theta. And this is your sector area, if your theta is in radians. Okay, and that's much nicer than this one. Just use half r squared theta. We don't even need to deal with pi. Okay, the fact that we're using radians basically sort of deals with pi for us. It's quite handy. So these two formulas, the arc length is r theta, and the sector area is half r squared theta, when your angle is in radians. These are two formulae that you should definitely try and remember. Unfortunately, they're not given to you in the formula booklet, but it's really useful that you remember these for when you're working on these sort of problems. Okay, so just going to look at a couple of examples here. These are going to be to do with arc lengths first of all. Let's find the length of the arc of a circle of radius 5.2 centimeters, given that the arc subtends an angle of 0.8 radians at the center of the circle. Here I've also written the word subtend. You might see that. It means opposite or beneath. I'll show you what this looks like as a diagram. It's my circle. Okay. So the circle is 5.2. in radius, so that's that length there. Then the arc subtends an angle of 0.8 radians. So I'm just going to put that in there, it's 0.8. Okay. And we've got to find the length of this arc here. Okay. So this arc subtends this angle of 0.8, it's opposite it. Okay. So we can just use r theta to find the arc length. So here it is literally going to be 5.2 times 0.8, which gives me 4.16. Okay, easy. Let's have a look at this next one. An arc AB of a circle with radius 7 centimeters and center O has a length of 2.45. Find the angle subtended by the arc. Okay, so we're going to do the same sort of diagram. It doesn't really matter if your diagram's accurate or not at this point, really. Radius is 7 centimeters on both, and it says the arc length is 2.45. And we need to find theta. So for this time, it's going to be, still use this formula. We know the arc length is 2.45. We know the radius is 7, and we've got to find theta. So theta is going to be 2.45 over 7, which is 0.35 radians. Okay. Right, here's an example with a sector area instead. So it tells me that the area of this sector, and it's just the minor sector, so that's the small bit, is 28.9 centimeters squared. The angle is 0.8, and we've got to find r. So the formula from before, sector area, is half r squared theta. So we know that half times r squared times 0.8 gives me an area of 28.9. And then we can just solve this equation to find r. So 28.9 divided by 0.8 times 2 square rooted gives me 8.5 centimeters. Okay, so easy so far, just using the formula and the information you're given. Okay, what would the arc length be for a circle of radius 1 and angle 1 radian? So radius 1, and this angle in here is also 1 radian. So the arc length is r theta. So that's going to be 1 times 1. So that would also be 1. So what this means in my diagram is this curved bit here, this has also got a length 1. And this is actually what defines a radian as being a radian. It is on a unit circle, so a unit circle being a circle with a radius 1. If you form an angle 1, the arc length here, this curved length, will also be 1. And that angle here is 1 radian. I've got a little animation I can show you about this as well. So here we've got our circle of 1 unit. There's its radius. And if we curve that radius around, so it's still got that, ours was length 1, then that is 1 radian. There's 2, 3 radians, and then you can see it's 3 and a bit radians, or pi radians for 180. And then a full circle is 2 pi radians. So you can watch it again, and this doesn't just work with a unit circle. If the radius is 1, then the arc length is 1, but also if you had a radius of 5, and then you'd be looking for the arc length to be 5 as well. So here they've just used r. So this radius is r. If we then form an arc length of r as well, like that, then this angle is always going to be 1 radian. Okay. All right, let's have a look at some more complicated problems that we might have to solve using this, not just finding lengths and areas and so on. Okay, So the border of a garden pond, which is this shape below, we've got a straight edge AB, which is this line down here, and that's length 2.4, and a curved part C. And this also forms an arc of radius 2 centimeters. Okay, so basically all this information is on the diagram. We've got to find the length C. Okay, so we've got to find this curved edge all the way around here. Now the most important information that we need to find out really, we've got R, so we just need to find out what is theta. Okay, well to do that I could try and work out this angle here, but I don't have much information to go on there. But if we just look at this triangle, so I'm just going to redraw the triangle at the bottom here. So if this length is 2.4, and this is 2, and this is 2, and we want to find a way of finding this angle at the top here, we could do it using the cosine rule, possibly, but I think that's going to be a bit complicated. The easiest way to do it is actually to split it in half, and then we could just use right angle triangle trigonometry instead. So if I split it in half, I then get a right angle down here. This length is obviously halfway, so it's going to be 1.2, and this diagonal is also 2. And I can try and find this angle up here. Maybe I'll call this angle X. So now I've got the opposite and I've got the hypotenuse. It's going to be sine. So sine X is 1.2 over 2. And then we can find X from that. And I'm going to do it in radians. So I'm going to make sure my calculator is actually set into radians at this point as well. If you need to do that, you just have to go to the setup menu on your calculator. And then you can go down to angle unit and change it there. So I need to do inverse sine of 1.2 over 2. And in radians, that gives me 0.6435 radians. So that's this angle here. So that means that this angle here is twice that. So I'm going to times that by 2. So it's 1.287. Now to find angle theta, well, that's going to be 360 in degrees minus this, but I'm not working in degrees, so it's going to be 2 pi minus 1.287. So 2 pi minus that. That gives me 4.996 radians. Okay, so theta is 4.996 radians, and now using that I can find my arc length C. So remember that the arc length is just r theta, so that is then 2 times 4.996. So that's going to be, well, approximately 10, but about 9.99. Okay, that's in meters. So you might have to do some simple geometry problems to help you along, normally involving a right angle triangle. And I've written that as a bit of a tip here. If you can try and get a right angle triangle in these problems, that's much, much easier than using the cosine rule. Okay, so do things like splitting a triangle in half will help you. Okay, so a plot of land in the shape of a sector of a circle of radius 55 meters. The length of fencing that is erected along the edge of the plot to enclose all the land is 176 meters. Find the area of the plot of land. All right, well, it tells me that the total amount of fencing along the edges, so that includes this curved bit, is 176 meters. So that must mean that the curved bit is 176 minus 55 minus the other 55, so that's 66 meters. So then in total it adds up to 176. So we know that the arc length is 66. So that means that r theta is 66. Okay. We know that r is 55. So actually we've got 55 times theta equals 66. So 66 over 55, 6/5 or 1.2 radians. That's my angle. Now to find the area, we can use the area of a sector formula, which is half r squared theta. So that's half times 55 squared times 1.2. So that is 1815 meters squared. Be my final answer there. Okay, so in this question, this is actually a past exam question, this one. But we've got this diagram here, and it's triangle ABC. So from A to B to C, this is a triangle with A to B equals 8, so that's this length here. A to C is 11, that's the big length there, and angle BAC is 0.7, we can see that on the diagram. The arc B to D, so notice that this is an arc, this is a curved edge, and this is part of a circle of radius 8. Okay, so the white bit is part of a circle, and then the shaded bit then turns this into a big triangle. Find the length of the arc B to D, that's the first thing. So this curved edge here is what we want to find. Well, we can use r theta, and here the arc length, r theta, is going to be 8 times 0.7. So you get 5.6 centimeters. So for part B, we have to find the perimeter of R. R is this shaded region at the top here. Now the perimeter of R, that's going to be the curved edge, which we've just found. So that curved bit there, which we said was 5.6, plus this length here, plus this length here, B to C. Now we can actually work out D to C, because A to D is also going to be 8 centimeters, because that's just the radius of the circle that forms this arc. So that's going to be 8 as well. So this little bit in here is going to be 3 centimeters. So now I've just got to work out length BC. And I think I'm just going to draw a triangle ABC again down here in the space, and just treat this as a triangle problem. So I've got 0.7 radians, I've got a length 8, and then I've got length 11 because I'm going all the way out to C, and then this length here, which I'm just going to call X. So I think the easiest way of solving this, because I don't know any other angles, so it's probably just going to be using the cosine rule. So A squared equals B squared plus C squared. That's 2BC cos A. Now our angle is in radians, so again, make sure your calculator is set into radians because we're going to have to do cos of the angle. In terms of labeling it, I'm going to make this A because I've got to do with angle A. So X is going to be side A. The other two don't matter quite so much, but I'm going to do 11 as B and 8 as C. So I've now got X squared is 11 squared plus 8 squared minus 2 times 11 times 8 times cos 0.7. Now I'm just going to solve this equation to find out what X is. And when I do that, just using my calculator, I get 7.098 centimeters. Okay, so let's put that on our diagram, 7.098 centimeters. So the perimeter of R is going to be 5.6 plus 3 plus 7.098. And it says just write it to 3 significant figures, so that's going to be 15.7. For the last part, we've just got to find the area of R now. So that's the area of that shaded region. Now to do this, our strategy is going to be to find the area of the triangle ABC, and then we're going to subtract the area of the sector. So then we're just left with that shaded bit. Okay, so we're finding the area of this shape here, and then we're going to get rid of this bit here. Okay, so let's find the area of the triangle ABC first of all. So basically we're finding the area of this triangle that I've drawn out here. Now, it's not a right angle triangle, so I'm just going to have to use half AB sine C. So that's half times 8 times 11 times sine 0.7. Okay, and you need to make sure that your calculator is in radians because you're doing sine of the angle 0.7. If I do that, I get an area of 28.346. Okay, so that's the area of the triangle. It's going to make area of triangle ABC. And then we want to find the area of the sector. ABD is the sector that we're looking at. So it's going to be half r squared theta. So it'll be half times r squared times theta, which is 0.7. We get 22.4. So then the shaded bit is obviously going to be the difference between the two. So 28.346 minus 22.4. That gives me 5.946. This is the three significant figures, so I guess it's going to be 5.95. There we go. Now what we did in the last question, where we did a triangle minus a sector, we're going to use a similar sort of approach for finding the area of a segment. So here a segment is the shaded bit, the bit that's shaded in yellow in this diagram. Okay, remember a segment is formed by a chord. Now, to find this shaded area here, I'm going to do the area of the sector. So I'm going to find the area of this, and then I'm going to subtract the area of this triangle. Okay, so let's do that bit by bit. So you've got the area of the sector. Sometimes it helps to draw a little sketch as well of this. So I'm finding this bit first. So that's 1.2, and this is 7. So the area of the sector is going to be half r squared times theta. Let's work out what that is. So it's going to be 29.4. And the area of the triangle okay, and again we've got 7, 7, and then 1.2. So this is the area of a triangle, so it's going to be half AB sine C. So it's half 7 times 7 times sine 1.2. It gives me 22.83. Okay, and the segment is obviously the sector minus the triangle. So 29.4 minus 22.83. So 6.57. Okay. Sometimes people would try and describe this as like a formula, because you can see the two things are quite similar. So you could write it as half r squared theta minus half r squared sine theta, if you wanted to, because this is the area of the sector minus the area of the triangle. And I suppose you could even write it as half r squared and then theta minus sine theta, if you wanted to. But I'm not sure if that's a useful formula to remember. What's more important is the strategy of how you find it. Okay, here's a different segment problem. So it looks the same sort of diagram. We know that the radius is 4 meters. And we know that this chord here is 5 meters long. We've got to find the shaded area. Now the problem here is we don't know the angle, so we've got to try and work that angle out. Now again, we could use the cosine rule, so we could look at this triangle OAB and use the cosine rule to find this angle here. But I think an easier way is to again split this triangle in half. So I'm going to split it like that, which will give me a triangle that looks like this, which is then a right angle triangle. So this would be 4. Then this height would now only be 2.5 because I cut it in half. And I want to find this angle here. I'm going to call this angle x, just so I don't get it confused with this theta here. So sine x is going to be opposite over hypotenuse, or 2.5 over 4. So x is going to be inverse sine of 2.5 over 4. Which gives me 0.675 radians. Okay, so then angle theta must be twice that. So that's 1.35. And now we've got a similar problem to what we had before. Okay, so I can do the area of the sector minus the area of the triangle. So it's going to be half r squared times theta for the area of the sector. And I'm going to subtract the area of the triangle. Half times r squared, or in this case it's 4 times 4 because it's half AB sine C, times sine 1.35. And then I can calculate what this is. When I do that, I get an answer of 2.99 meters squared. Right, so this idea of splitting things into right-angled triangles is still really useful in these sort of problems as well. Okay, last one. So in this last question, we've just got purely an algebraic question here. Now let's just make sure we understand what's going on in this diagram first. So AB is the diameter of the circle, and the radius is r. And BOC is theta, so yes, this angle they've marked in here is theta. Given the area of AOC, so that's this shape here, this triangle here, is 3 times that of the shaded segment, show that this is true. Well, I think before we go any further, something that we can do is label this length here. If this is the center of the circle, then O to C, that must be a radius as well. So this length here is also going to be r. I think that's going to be useful. Now the area of AOC, okay, so triangle AOC, it says is 3 times that of the shaded segment. I'm just going to write 3 times the segment. Okay, then we can fill in as much as we can know about this diagram. So a triangle AOC, so we can just find this using half AB sine C for the area. This angle here, we don't know it, but obviously this is a straight line. If we were working in degrees, we would say 180 minus theta. But here, because we're in radians, we're going to do pi minus theta for that angle there. So this is half AB, which is r times sine pi minus theta. And that equals 3 times this segment here. Now we found segments several times before, so we can do the area of the sector, which is half r squared theta, subtract the area of the triangle, which is half AB sine C. So again, that's going to be half r squared, because they're both r, so r times r, sine theta. Okay, and that's our equation, and hopefully we can rearrange this to get to this result that they want. Right, let's try and just tidy it up a bit because it looks a bit messy at the moment. So I'm going to simplify the left-hand side to half r squared sine pi minus theta. And here I've got lots of r squareds and half r squareds in here, so I'm going to actually factor out the half r squared. So this is going to become 3 over 2, because I'm going to pull the half out, 3 over 2 r squared times theta minus sine theta. Okay, so I've got it like that. Now what I'm going to do is I'm going to get rid of, well, divide through by the half and the r squared, because that appears on both sides as well. So I'm just going to be left with sine pi minus theta equals 3 theta minus sine theta, like that. Okay, well, that's kind of looking like this. I've got sine pi minus theta equals 3 theta minus 3 sine theta. Well, it doesn't quite look like this, does it? But it's got the 3 theta and it's got 3 sine theta rather than 4 sine theta. We need to think quite carefully about this. Sine pi minus theta. Maybe think of this as sine 180 minus theta, if that helps in degrees. Now, when we're finding solutions on the sine graph, first think in degrees. Sometimes that's easier, so we're more familiar with it. If we wanted to solve it, and this was my first answer, the second answer would then be 180 minus that one. Okay, so if this is theta, this one here would be 180 minus theta. So that means that sine theta, maybe this value here was, I don't know, 0.6 or something, would be exactly the same as sine 180 minus theta. So actually this is exactly the same value as sine theta. And now we can make this final step that they need. So you can subtract sine theta from both sides. And then we've got to our result. Okay. So a little bit more complicated, but that's definitely one of the harder exam questions. Now for some practice, if you have a look at exercise 5D, you can probably start on question 6 onwards and just focus on sort of the exam style questions in that exercise to practice.